November 11th, 2025. A seemingly ordinary day in our observation of the cosmos, yet what unfolded in the skies that day challenges everything we thought we knew about comets. The object known as 3I, Atlas, a visitor from the depths of interstellar space, has confounded astronomers with behavior that is as baffling as it is extraordinary. Images captured just days before had suggested one story, yet new observations tell a completely different tale. For years, astronomers have tracked comets within our solar system, understanding their behaviors as predictable. As a comet approaches the sun, heat and radiation cause ice to sublimate, forming jets of gas and dust that stretch out into the characteristic tails we associate with these icy travelers. But 3I Atlas has been rewriting the rules. On November 9th, telescopic images revealed tails extending millions of kilometers in both sunward and anti-sunward directions. Such tails, by the laws of physics, imply that the comet has been ejecting gas at roughly 1,500 kilometers per hour for months, yet images from only a few days prior showed no such tails. The mathematics quickly became alarming. For the tails to appear as they did, 3I Atlas would require an active surface area of approximately 1,600 square kilometers. To put that in perspective, this is the surface area of a sphere roughly 23 kilometers in diameter. Observations from the Hubble Space Telescope, however, measured 3I Atlas at only 5.6 kilometers across. The calculations suggested the comet needed to be almost 4 times larger than it physically is. Even more troubling was the mass loss implied by these tails. Estimates indicated that 3I Atlas must have been shedding around 50 billion tons of material per month, despite the comet itself being calculated to weigh roughly 33 billion tons. These numbers alone seemed impossible. Historically, when comets have appeared to lose more mass than their total estimated weight, the explanation has been fragmentation. The most famous example is Comet Shoemaker-Levy 9, which broke into 21 pieces in 1992, dramatically increasing its total surface area and accelerating sublimation. It seemed logical then that 3I Atlas had fragmented. 7 jets had been observed on November 8th, paired with massive multi-million kilometer tails. The object should have been breaking apart before our very eyes. Yet, 2 days later, the story took a dramatic turn. Astronomers David Jewett and Jane Liu pointed telescopes in the Canary Islands at 3I's Atlas and released a report titled simply, 3I saw Atlas, still single. What did they find? A single bright nucleus, the solid core of the comet, surrounded by a glowing, active coma of gas and dust. The coma was intricate, with structures and flows indicating intense activity. 2 tails extended in opposite directions, one pointing almost directly at the sun, forming a rare anti-tail, and the other pointing away from the sun in the conventional manner. Their measurements were precise. The anti-tail was offset by only 9 degrees from the sun's position. The astronomers didn't just glance at the images. They examined a vast region around the comet, 500,000 kilometers across, employing every tool available. Brightness levels were stretched, contour maps created, false color overlays applied, and radial analyses conducted. Every technique was aimed at uncovering even tiny fragments, and the result was unequivocal. No pieces, no debris, no signs of fragmentation anywhere. 3I Atlas had survived its closest approach to the sun intact, unbroken, continuing to produce extraordinary jets of material in multiple directions. This discovery deepens the mystery. 3I Atlas passed perihelion on October 29th, the point in its journey where thermal stress and solar radiation were at their peak. The object should have fractured under the pressure of rapid sublimation. Theoretically, the jets alone, ejecting massive amounts of material, could have torn it apart. Yet, here it is, fully intact. Scientists are now exploring potential explanations. One hypothesis relates to the comet's age. 3I Atlas may be almost billions of years older than our solar system itself. Traveling through the cold, dark reaches of interstellar space for 7 to 10 billion years, during this immense journey, it has been bombarded by cosmic rays, high-energy particles capable of altering surface chemistry. These rays may have transformed carbon monoxide into carbon dioxide, creating an unusually high CO2 to water ratio. This chemical transformation may have also produced a crusty surface layer, insulating the underlying ice and channeling sublimation in unprecedented ways. Another possibility is that the mathematics themselves may need refinement. The calculations suggesting mass loss of 50 billion tons per month are based on tail brightness and size. Perhaps these tails are exceptionally effective at scattering sunlight, appearing more massive than they actually are. Even if the real mass loss is only 1/10 of previous estimates, the comet's behavior remains extreme, yet physically plausible. Still, the precision of these methods, honed over decades of comet observation, suggests that the anomaly is real. 3I. Atlas is shedding enormous amounts of material without breaking apart. Its internal processes, or the way sunlight interacts with its surface, may be fundamentally different from anything we've observed before. Observing 3I, Atlas challenges our understanding of cometary physics, of mass loss, and of the long-term effects of cosmic radiation. It forces a re-evaluation of how interstellar objects behave when they encounter the heat and pressure of a star for the first time in billions of years. Unlike any comet we've studied, this object survives extreme conditions intact, exhibiting activity that would have destroyed ordinary comets. Some researchers speculate that internal channels or pockets of ice may concentrate sublimation in ways that magnify jet activity without threatening structural integrity. Others propose that cosmic ray-induced crust may act as a pressure valve, allowing gas and dust to escape efficiently while stabilizing the nucleus. The truth is, we are witnessing a physical process in real time that does not fully align with any model we currently possess. 3I. Atlas also reminds us of the incredible variety of objects traversing the cosmos. Interstellar visitors carry histories, chemistry, and structures that are alien to our solar system. Each discovery stretches the boundaries of knowledge, highlighting not only what we understand, but also how much remains hidden in the vastness of space. As telescopes continue to observe, and as instruments like the James Webb Space Telescope analyze its composition in detail, the comet's ongoing activity will be closely monitored. Every jet, every tail, and every flicker of brightness provides new data for scientists trying to unravel the mystery of how an object can survive what should be catastrophic conditions. Ultimately, 3 Atlas challenges a fundamental assumption that extreme mass loss necessarily leads to fragmentation. It may be demonstrating that comets, especially interstellar ones, can behave in ways that defy conventional physics, surviving extreme environments while producing activity far beyond what size and mass suggest is possible. The implications are profound. If 3I Atlas maintains its integrity while shedding material at unprecedented rates, it may alter our understanding of cometary evolution, of interstellar travel, and of the diversity of physical structures that can exist in the universe. Every observation forces a re-evaluation, not just of comets, but of how matter behaves under extremes of heat, radiation, and cosmic age. We are left with more questions than answers. How can a small, 5.6-kilometer wide comet endure the equivalent of solar oven conditions without fragmenting? What internal structures allow it to channel sublimation so effectively? Could other interstellar objects be waiting to challenge our models in ways we cannot yet predict? 3I. Atlas reminds us why the cosmos is a place of wonder and mystery. Every object we study carries stories older than our own planet, lessons about physics stretched to the limit, and examples of nature operating beyond the boundaries of imagination. The comet continues its journey outward, still intact, still mysterious, still an enigma. As astronomers track its progress through space, it offers a rare opportunity, a front-row seat to processes that have never before been observed in human history. The images, the measurements, and the calculations collectively pose one of the most compelling astronomical puzzles of our time. November 11, 2025 may be remembered not just as a date when new images were captured, but as a day when 3I Atlas redefined what is possible for interstellar visitors, leaving the scientific community grappling with questions that may take decades to answer. Its survival and activity will continue to inspire research, debate, and awe, reminding us that even in a universe that is largely predictable, there are phenomena that remain fundamentally unpredictable.